We're dealing with the knowledge area, electricity and magnetism. The section we're looking at now is current electricity, and I have additional questions on this section. Right. A steady current of 2.5 amps exists in a wire for 4 minutes. Right, there's the duration. How much total charge passes a given point during the 4 minutes? Right, and how many electrons would this be? Okay, let's look at it. Now we know I is equal to Q upon change in time, which I use a symbol notation to say that implies Q is equal to I times change in T, right? Which would mean that our current is 2,5 amps. Our change in time would be 4 minutes, right? Times 60 seconds, right? Which would then be 600 coulombs. Okay? Now we want to know how much or how many electrons are moving past the fixed point. We have N is equal to Q upon E, right? We're dealing with electrons. And that would mean 600 coulombs. We know what the charge on an electron is. It's 1.6 times 10 to the minus 19 coulombs per electron, right? And which is then equal to 3.75 times 10 to the 21 electrons. Okay? Electrons. That is the amount of electrons that pass a fixed point during that 4 minutes. Right, now let's look at a small flashlight bulb that draws 300 milliamps from its battery. Okay, so we're looking at, let's just go back here. So this here would be A, and that would be B. That would be B. So that's B. Okay. Right, now we look at a flashlight bulb. This particular bulb draws 300 milliamps from its 1.5 volt battery. We want to know what is the resistance, right? And if the battery becomes weak, that means the chemical reactions in it are not, the rate is not fast enough, and the voltage drops to 1.2 volts, how would the current change? Okay, this is a fairly simple one. So we say R is equal to V upon I, right? The voltage, and we want to know what the resistance is, which means we have the voltage of the battery, which is 1.5 volts, and the current is 300 milliamps. So it's 300 times 10 to the minus 3 amps. Right. And that is equal to 5.0 ohms. Okay. So that is the resistance. Right. Now we want to know what would happen to the current if, for instance, the battery voltage drops to 1.2 volts. Okay, so there we have that. And B, if it drops to 1.2 volts, so we know I is equal to V upon R. If the battery voltage drops to 1.2 volts, and it can drop, like I said, if the rate of the reactions in the battery have slowed down, and the resistance is a property of the battery, and that remains the same, which would then mean 5.0 ohms, which that means 0.24 amps, which is the same as 240 milliamps. Okay, so the current then reduces from 300 milliamps there to 250 milliamps as the battery reactions in the battery slow down. Right, now let's look at the next one. A service station. Okay, the service station charges a battery. Okay, this is now charging the battery, right? And in doing so, it uses a current of 6.7 amps for 5 hours. Right, there's the reverse of discharging. When a battery supplies current to the external circuit, it's like discharging. Here is the opposite process. When a battery is flat, we use a charger, and the charger is supplying 6.7 amps. How much charge passes through the battery? So we say, okay, I is equal to Q upon change in T, right? Which implies Q is equal to I times change in T, change in time, which means it's 6.7 amps times 5 hours. Convert hours to minutes, we multiply by 60. Converting minutes to seconds, we multiply again by 60. And that would mean we got, right, 120,600 coulombs. Okay. Which is equal to 1.2 if I leave it like that and say it's times 10 to the 5. Okay, equivalent coulombs. Okay, now let's look at the next one. Here we want to know what is the current in amperes if 1200 Na ions, sodium ions, sodium which has lost an electron, so it's positively charged, so these are cations, and they flow across a cell membrane, and the time it takes is 3.5 microseconds. The charge on the sodium ion, there it says, is the same as the charge on an electron. Okay, so it's the same charge, it's just that the one is positive and the other one is negative. And we want to know now what is the current in amperes. Now, essentially, what we have here is it's like, say, you have your membrane, right? And you got your sodium ions that are moving through the membrane, right? And you know the cell membrane has got an intracellular, it's intracellular, right? And outside is extracellular, cellular, okay. And what happens is you got your sodium ions that move either from outside the cell and it moves into the cell, or it may move out of the cell. And we want to know if we got 1,200 ions flowing across the cell membrane, what is the current? So we say, okay, I is equal to Q upon change in time. Current is, so we got we have 1,200 Na particles, and we know that the charge is 1, right? 1.6 times 10 to the minus 19 coulombs, okay? And that happens for 3.5 micro, so micro is 10 to the minus 6 seconds, which means that the current that's moving through here is 5.5 times 10 to the minus 11 amps. Right, that's the current moving through that cell membrane. Now you know, I mean, our entire system, our neuro system, our nervous system deals with ions actually moving past membranes. And furthermore, also your heart, I mean, whilst it looks like it's a mechanical organ, it's actually an electrical organ. And when these charges move in the cell membrane, what happens that if the concentration of the ions in the extracellular part is greater than the intracellular part, what happens is a cell voltage is set up, right? So even in the heart, you find that the heart beats, but there's a potential difference between the concentration of the ions in the respective side of the membrane. Right, so we essentially are like electrical devices, looking at it very differently. Right, now if we look at the next one, what is the resistance of a toaster if 120 volts produces a current of 4.2 amps? Okay, so what is the resistance? R is equal to V upon I, right? And then we have that is equal to, the voltage is 120 volts, okay? And the current is 4.2 amps. And that gives us 28.57 ohms. Okay, so that is the resistance of the toaster. Right, now let's look at the next one. We have a 9-volt battery connected to a bulb, right? Whose resistance is 1.6 ohms, right? And how many electrons leave the battery per minute? So essentially what we're saying is, here we got a 9-volt battery, it's 9 volts, and that is connected to a bulb which we can draw like that, okay? But normally when I draw it, I just put it as a resistor, all right? But we can draw it like that, and we find that the bulb has a resistance of 1.6 ohms and the battery is 9 volts. So now we want to know how many electrons leave the battery per minute. So if we're looking at electrons, that means we're looking at electron current, and we saying how many electrons move in that direction, right? If we dealt with conventional current, we would have moved from the positive to the negative. All right, but we mostly we deal essentially with conventional current, but it doesn't matter because our answers should be the same. The magnitude of our charges that move past the respective electrodes. So if we look at that, we say, okay, I is equal to V upon R, which would mean 9 volts upon 1.6 ohms, which would mean then it's 5.625 amps. That is the current that's being drawn by that particular resistor. All right. So we want to know how much charge is that. So Q would be equal to I times change in T, which would mean 5.625 amps times the time is equal to, right, 1 minute, so that's 60 seconds, and that would be 337 337.5 coulombs. Okay, that's the amount of charge that it would be leaving that negative electrode. So we want to know now how many electrons leave that electrode. So we got N, right? We say, okay, N is equal to Q upon E, which is then equal to 337.5 coulombs all upon 1.6 times 10 to the minus 19 coulombs per electron, right? Which then is equal to 2.1 times 10 to the 21 electrons. So many electrons leave that negative terminal in 1 minute. Okay, let's go to the next one. What we have here? Oh, a bird stands on an electric DC transmission line. And this transmission line carries a current of 2,800 amps, right? But the line has a resistance of, the resistance is low, 2 times 10 to the 5 ohm resistance per meter. That is the resistance of the line. And normally these transmission lines have to have very low resistance because you want to minimize heat loss. If energy is dissipated in the surroundings, then we can't make we need efficient transmission of current. So that is why one of the reasons is we the resistance of that transmission line has to be low, right? And that's why we have step-up transformers that you'll deal with in grade 11 and 12. Okay, now, so what do we have here? But we have this bird, and this bird's feet is 4 centimeters apart. What is the potential difference between the birds? Right? What is the potential difference between the bird's feet? It's supposed to be. Right? Okay, between the bird's feet. Right, now, if we look at this, we say, all right, here we've got our bird. Okay, say we have our bird. Say we have our bird. We have our bird here. And let's say here's our bird. And let's say there's our bird. And there's our bird. Okay. And this bird here is on a transmission line there, standing there. And the distance between these 2 feet is 40 centimeters. Okay, 40 centimeters. Okay. Right, but now we want to know what's the voltage between these 2 feet, because so we got now R is equal to V upon I, right? Which obviously implies that V is equal to I times R, right? So what is our current? Okay, like that. Our current is then equal to, so V is equal to 2,800 2,800 amps, right? And our resistance is going to be 40 centimeters, so which is times 0.04 meters, right? Times 2.5 times 10 to the minus 5 ohms per meter. So, okay, that's going to cancel out, and then what is our voltage? 0.0028 volts between the bird's feet. Right, so this is a relatively small voltage, right? And that is one of the reasons why the bird does not get shocked. It has a very small voltage between its legs. Right, and you see these birds on the transmission lines, they can stand without getting shocked. Essentially, that's because the voltage between the feet is extremely low, right? Well, it doesn't harm it physiologically. Right, now let's look at the next one. So here if all you have is a 120 volt line, would it be possible to light several 6 volt lamps without burning them out, right? And how would we do that? Okay, so we know it's a 120 volt line, and the lamp operates on 6 volts, but we've got several of these lights, so how do we connect them, right? What comes to mind, we know that when we connect lamps in series, they are potential dividers. So you think about connecting them in series. So you have now your 120 volts, right? You got 120 volts, and here you've got your resistance that's gonna go through like that, and we don't know how many of those, right? But we know that we want across each resistor a voltage of 6 volts. That's what we want, because that is the voltage that that particular lamp functions. So if we have that now, we got our number of bulbs would be, say, number of bulbs, okay, would be equal to 120 volts all upon 6 volts, right, per bulb, which would then mean we have 20 bulbs. So we got 20 bulbs, which essentially means if we have 1 bulb, 2 bulbs, 3 bulbs, 20 bulbs in series, we're going to have then each one having 6 volts, and it would then function efficiently. Right. So now we look at two light bulbs of resistance R1 and R2, and it says R2 is greater than R1, and they are connected in series. Okay, and the question is, which is brighter? Right, two, they connected in series. Then what if they are connected in parallel? Which is brighter? Explain. Right, so you could use calculations to do that, or you could just do it qualitatively by using formulae. So if we say I have this, say that, and whatever the voltage is, we got R1 and we got R2, like that, as R2, and we know R2, and we know that R2 is greater than R1. Right, now we know that R2 is greater than R1, and the voltage across both these resistors must be equal to the cell voltage, right? So since R2 is greater than R1 and the voltage is the same, we would say that V is directly proportional to R, right? Since here we have a voltmeter there and we'll have a voltmeter there, right? Both of them must give us a cell voltage, but R2 would have a greater potential drop than R1. And because of that, it's the same series current going through, we would then say R2 is brighter than R1. Same current going through, higher voltage across it, and we find that it would be brighter. We can even relate the brightness to power, but power doesn't, that you'll deal with in grade 11. Right, now let's look at the next one. Here we have again the same battery, but this time we have R1, okay, and we have R2 connected here, okay. So if we have this, we know that the voltage across the resistors remain the same. So we know voltage, okay, across the parallel branch is the same, right? And we know that in here you got your current in the circuit, and when you have your current in the circuit, you're going to have I1 going there and I2 going through there, right? It branches out. And I had indicated that the conservation of charge, the law of conservation of charge applies, right? Which would then mean, if we look at this here, and we know that R2 is greater than R1, which then implies what? If R2 is greater than R1, it would imply that R2 will have less current than I1, which implies that I1 is greater than I2, and is the same voltage across both the resistors. And if that is the situation, we then say R1 is brighter than R2. There you go. Right? Okay. Now, if we look at the next one, and it says we've got 45 ohm light bulbs and 75 ohm light bulbs, and these are connected in series. So what is the total resistance of the circuit? Right? What is the total resistance of the circuit? Okay, so if we look at that here now, we say, okay, we've got this, right? We got that, and here we say, okay, 1, 2, 3, 4, 5. Sorry about that. 1, 2, 3, 4, 5, 6, going like that, right? And this is 45 ohm. That's 45 ohm. And that's 45 ohm. And that is 75 ohm, 75 and 75 ohm. So we want to know what's R total. R total would be let's say we could call this R1, R2, R3, R4, R5 and R6, which means it would be R1 plus R2 plus R3 plus R4 and R5 plus R6, which would mean it's 45 ohms plus 45 ohms plus 45 ohms, right? Right, and that, if you add it up, gives us 360 ohms. Okay, so that's you just need to add it up, and that gives you 360 ohms. Now we want to know what happens if these are now connected in parallel. And if they're connected in parallel, then surely we're going to have this like that, and that would be 1, 2, 3, right? And all these would be 45 ohms. And then another 3, okay? And that would be 75 ohms, right? So the top 3 is 45, and that would be 75 ohms, right? Which means if we look at this, right, these 3 would be 75 ohms, that 3 would be 45 ohms, okay? So which means 1 upon R total is equal to 1 upon is equal to 1 upon R1, let's call it also R1, plus 1 upon R2, plus 1 upon R3, plus 1 upon R4, plus 1 upon R5, plus 1 upon R6, right? Which is obviously 1 upon 45, plus 1 upon 45, plus 1 upon 45, okay, and 1 upon 75, plus 1 upon 75, plus 1 upon 75. So if we want R total, we could just take the inverse of that, and that would give us 9.37, 9.375 ohms. Okay, so you also need to know how to use your calculator. So I mean, if you've got an answer there and you want a reciprocal for it, you need to know where your reciprocal button is so that you can work out what the R total is. It's important for you to know your calculator very well. So you need to, for instance, work out certain calculations and see whether what you're getting is correct, because sometimes you may think you having the sequence right and it may not be correct. So you need to know your calculator very well. Right. Now we look at suppose you have a 680 you have a 680 right, a 940, and a 1.2 kilo ohm resistor. So we want to know what is the maximum, right? We know that in this sort of situation, if you want to know what is the maximum, then we have to connect it in series, right? So we say, okay, we're not given the voltage, so it doesn't matter, because resistance is a property of that particular material. So we got that, and we got that, and we have that. Huh? And one is 680, one is 680 ohms, the other one is 940 ohms, and the other one is 1.2 kilo ohms, which is 1200 ohms, right? And if you want R total is equal to 680 ohms plus 940 ohms plus 1200 ohms, which then gives us 2820 ohms. That is a total or maximum total resistance. If you want the same thing with the same battery, okay, but not that the batteries matter in this particular case, because we not looking at current, we only looking at the resistance. Alright, so that is 680, that is 940, and the other one is 1200 ohms. Okay, so that's 680 ohms, and that's ohms. So we know 1 upon R total or R parallel is equal to 1 upon, if we could call the first one R1, so we can say R1 plus 1 upon R2 plus 1 upon R3, okay, which would then mean that is equal to 1 upon 680 plus 1 upon 940, right, plus 1 upon 1200. And if we want R total for that, we do the same thing, take the inverse of that, and that should give us 300 ohms. Okay, there you have that. Right, now let's say we now have a 6-volt battery, okay? But you only wish to apply a voltage of 4 volts. Right. So given an unlimited supply of 1 ohm resistors, how could you connect them so as to make a voltage divider? We know if we want a voltage divider, we have to connect them in series, right? And that produces a 4 volt output for a 6 volt input. Right, so what happens, you got now a 6, you have now a battery, okay, and it is 6 volts. But what happens is that you've got some element here that works, but it only requires 4 volts. That is what, but a battery can supply 6 volts. So we want 4 volts, right? And you're given an unlimited number of resistors. Right, you can connect as many resistors here, as many as you want. But what you do want is that cell voltage, 4 volts must be dropped across this element because it can operate with a voltage of 4 volts. So we want to know, we can see immediately that whatever resistor we have, it has to have a voltage of 2 volts, right? So that 2 volts plus the 6 volts give us, 4 volts plus the 2 volts give us 6 volts, right? So let's maybe call this AB and let's call that CD, okay? If we look at this here now, we can say that the voltage of the battery, right, is equal to voltage across AB plus voltage across CD. Okay, but if we want to know what the voltage across CD, I've already preempted that, which means voltage of the battery minus voltage across AB, which would mean it is 6 volts, right, minus 6 volts, 6 volts, it is 6 volts minus 4 volts. That means CD must be 2 volts. Okay, 2 volts. There we have CD must be 2 volts. As I've shown you there, it has to be 2 volts. Okay, there, right, as we've indicated. So it's 2 volts. Right, now if we look at it, since current in the series circuit is the same, okay, since current in the series circuit is the same when the resistors are connected in series. Okay, now if we look at I in a circuit, right, if we look at the I in a circuit, say if I look at the I in the circuit, it's going to be equal to VAB upon RAB. Okay, and which is equal to V across CD upon R across CD. So thus we have here 4 volts, right, upon RAB is equal to 2 volts upon RCB. Okay, so which implies what? Which implies, if I look at this would imply that RAB, right, is equal to 2 times RCB. Right, so what it's saying, the relationship between RAB and RCB is RAB is equal to 2 RCB, which essentially would mean if I take a resistor of 1 ohm RAB, then that has to be, if I take if I take RCB to be 1 ohm, so say 1 ohm, then RAB has to be 2 ohm. If I take RCB to be 2 ohms, then RAB has to be 4 ohms. So RAB has to be double RAB has to be double RCB. So if we can say, for instance, let's say RCB. Okay, let's not go there because I have indicated that. So then current, okay, then current, right, in circuit, okay, we can say I is equal to, now we got still 6 volts, correct? But if we take this relationship and we say, okay, I am taking this to be 1 ohm, and that is 2 ohms, which means it's a total of 3 ohms. So if I take that to be 3 ohms, I find my circuit current is 2 amps. Right. So now if 2 amps is my circuit current and I want to know what is my voltage drop across that, so now we say, okay, which I can do that, I'm just showing you, which says now V across AB is equal to I in the circuit times RAP, which would then mean 2 amps and the resistance is 2 ohms. So now the voltage across that would be 4 volts. Right. And you can check across CD, it would be again, it would be then equal to, say we want the voltage across CD, it would be I in a circuit, the same thing, R across CD, which would mean we know is the same circuit current times 1 ohm, and it means the voltage would be 2 volts. Right, so we know, okay, we've got the voltage 4 volts across that particular element, and it should be functioning effectively. Right, we could have did this, but I've just illustrated it using formulas. Right, so now let's look at the next one. If we look at, say here, we have, suppose that you wish to have a supply of 0.25 volts potential difference between 2 points. Whoa, on the human body. That's the voltage you want, okay? But the resistance of the human body is about 2000 amps, right? That's, when your body is wet, the resistance is lower, but when your body is dry, the resistance is higher, and then the resistance in different parts of your body is also different, right? And we only have a 9-volt battery. So how can you connect up one or more resistors to produce the desired voltage? What voltage do we want across the human body? 0.25 volts. Okay. So here we have our battery, which is 9 volts, and we want to now have a resistor there, right? And we don't know what that resistor should be, but here we got this person this human body, and the resistance of that is 2000 ohms. And what we want is a voltage across this and there to be 0.25 volts. That's what we want, right? We want a voltage of 0.25 volts, but let's just do it a bit better. So here we got this and there we got that, okay? And we want a voltage of sorry about that. We want a voltage of 0.25 volts. That's what we want. But our battery is 9 volts. So we know the voltage across this will have to be in this situation would be have to be 9. So let's say V1, if we can call it V1. V1 is equal to 9 volts minus 0.25 volts, which means it has to be equal to 8.75 volts. So this will have to be a voltage of 8.75 volts, right? So if we want to know what's the current in the circuit, I in the circuit would have to be across the body is 2.5 volts, which is fine, all upon it has a resistance of 2000 ohms, which then means that is equal to 0.000 0.00125 amps. Okay? Or it's 1.25 times 10 to the minus 4 amps. So that is a current that goes through the human body. Right, but we know what current we have there, and the human body and this resistor are connected in series, right? So resistor plus human body connected in series. Okay, they're connected in series. And therefore, now we want R, okay? So R, the resistor, is equal to V upon I, but we know the voltage there has to be 8.75 volts, and the current that we want is 1.25 times 10 to the minus 4, 10 to the minus 4, 10 to the minus 4 amps. Okay, so what should that resistance be? If you work that out, that would give you 70,000 ohms. Okay, which is the same as 70 kilo ohms. So if you want to have a current of 1.25 times 10 to the minus 4 amps going through the body, and it's having a potential difference of 0.25, you have to put a resistor in series, and the magnitude of that resistor is 70 kilo ohms. Right, let's look at this question. Suppose a person's body has a resistance of 950 ohms. We want to know what current passes through the body when the person is accidentally connected to a 110 volt source. Okay, so let's look at that. So let's say we have a battery with 110 volts, and we have a person, right? Okay, yeah, and the resistance is 950 ohms, right? And we want to know what current passes through the person. So let's say we say I through the person. Here's a resistance of 950 ohms. Say voltage of the source over the resistance of the person, which would give us now 110 volts upon 950 ohms, and that would give us an equivalent of 1.12 amps, right? Which is equal to like about 120 milliamps. And 120 milliamps can be quite fatal if it passes through our body. Right, now let's look at the next one, where we say if there is an alternative path to ground, and we look at that, and that is like a parallel connection, and the resistance is 45 ohms. We want to know what current passes through the body. So if we look at that, and if we look at this particular connection, so let's say for instance now we have that, and we have a resistor here, and that is 45 ohms. Okay, so we get our current coming through like that, and like that, and some go there and some go there. So we know that in this circuit, when we have parallel connections, the voltage is the same, and they are actually current dividers. But in this here, if we want to know the current through the 950 ohm, it will still be V of the source, which would mean V of the source, right, upon R 950 ohms, which means still 110 volts, all upon 950 ohms, which would still be 0.12 amps. Right, I've rounded that off. Now let's look at the next one. If we have this voltage source, and it can produce at most 1.5 amps, right? So it can produce at most 1.5 amps. How much current passes through the person? Okay, so we say, all right, we need to calculate now we need to calculate what our total resistance is. So if we want our R in a parallel branch, that would be R, right, 950 ohms, okay, times R 45 ohms, all upon R 950 plus R 45 ohms, right? Which would then mean, if we look at this, this would then give us 42.96 ohms. That would be now the resistance of that circuit. Right, so now we know that at most the voltage, at most the current that can be supplied is 1,5 amps. So let's work out what the voltage would then be. Right, so the voltage of the source that provides 1.5 amps, okay, which would mean V of source is equal to I, which is 1,5 amps, times 42.96 ohms, which then means it's 64.35 volts. So that's the voltage of your source, which if it can supply 1,5 amps. But now we want to know what current will go through the body. So we say I across the 950 ohm is equal to V in a parallel circuit upon R resistance of the body, which would mean in this case it is 64.35 volts, all upon 950 ohms, and that gives us 0.067 677 amps, which then is equal to 60, equivalent to 68 milliamps, and that's still quite a high current as well, right? It can make your muscles contract when current is passed through your body. Right, now let's look at this from an alternative perspective. So if I have, let's say, let's look at it alternative perspective. So alternative solution, right? Okay, so what we do know is that the voltage across that and that is the same voltage, and that is the voltage of the source. So we can say V of 9 across the 950 ohm resistor, right, is equal to V across the 45 ohm resistor, okay, since they are in parallel, right? Since resistors in parallel. Okay, now if we look at this, we say, all right, let's expand it a bit further, and we say I, right, 950 ohms times R of the 950 ohms is equal to I in a 45 ohms times R the 45 ohms. Right, but okay, but we know that I, the total current, is equal to I in a 950 ohms plus I in a 45 ohms. Isn't it so? Because, I mean, if we got a total current here, there's a certain amount that's going to go through there and there, but we know that will have to be equal to I total. Right, so if you look at that now, we say, all right, therefore, since I total is equal to that, if we want to now know what is I in the 45 ohm, that would be equal to I total, right? Minus I in a 950 ohm resistor. Right, so that is what we have there. Alright, why am I doing that? Essentially because now let's use we got I 950 ohms times R 950 ohms is equal to I in a 45 ohms times R in a 45 ohms, right? So if we look at this here now, we say that I 950 ohms times R 950 ohms is equal to, we do this now, we see what I in the 45 ohm is the same as I total, right, minus I in a 950 ohms, and that is multiplied by R 45. Right, so if we look at this now, and which then gives us I 950 times R 950 ohms, which is equal to I T R 45 ohms minus I 950, right, times R 45 ohms. Okay, right, so what we can do here is get I, right, we got I 950 ohms times R 950 ohms, and here this term we can bring it on that side, okay, which means plus I 950, right, times R 45 ohms, right, and which is equal to I total R 45 ohms. Okay, so if we have that, we can then take out I 950 ohms, and we then left with R 950 ohms plus R 45 ohms, right, and which is equal to I total times R 45 ohms. Okay, so which then means if we want to know what is I in a 950 ohms, that means that person that has a voltage of a resistance of 950 ohms, which would then be equal to I total times R 45 ohms all upon R 950 plus R 45 ohms, right. So that now what's our total current there, the maximum is 1,5 amps times 45 ohms all upon 950 ohms plus 40 plus 45 ohms, which would be 1,5 amps times 45 ohms all upon 995 ohms. And if we worked that out, that gives us 0.067 677 amps, and which is then equivalent to 68 milliamps. There you have it. Right. Just use an alternative approach here, and you can see in this approach we didn't have to worry about what the voltage of the battery is, and as long as we knew what the maximum current was, we could then determine what current goes through the person. Okay, let's go to the next one. Here we have a circuit, and it has three identical bulbs. Each has a resistance of R, right? Each one having a resistance of R. We want to use minimum mathematics. Okay, so that means you just want to see your qualitative understanding of this, but we still have to use some mathematics. So when the switch S is closed, how will the brightness of bulb B and C compare with that of bulb A? So here that switch is closed, right? And we want to know how will the brightness of the bulbs compare. Okay, so we can now look at this, and let's say when switch S is closed. Okay, so what we do know, if switch S is closed, if current goes there, it's going to split there and it's going to split here, right? Alright, so we know we have, let's say in bulb A, so we say current in bulb A is going to be equal to current in bulb B plus current in bulb C, right? And since R of bulb B is equal to R of bulb C, what we can say that therefore IB is equal to IB is equal to IC. Right, so in the B and C, the current would be the same. But obviously, the current in bulb A would be greater, as this relationship shows you. Alright, so this implies that IA is greater than IB, but IB is equal to IC. Isn't it so? So, if we then look at brightness, and if we're relating it to that, which would then mean, in this case, we would find that if we relate this to bulb A, right, and that bulb B and that bulb C, we would know that A brightness would be greater than B's, and B's is equal to C. Right, so it would be that option. Isn't it so? Right, now we say we want to compare the brightness of bulbs A and B when S is opened. Okay, so when S is now open, here, that means what we're going to have is there's going to be no current going through here, no current there, but there is going to be current going through here, there, and it goes right through our circuit and it gets back there. But we know also that bulb B and bulb A and bulb B in this situation, they are in series. And what do we know about when bulbs are connected in series? It is the same current, there's one conducting path, and all we know is that when resistors are connected in series, they are potential dividers. But in this case, since bulb A and bulb B are identical, they will have the same voltage. Is it not? Because if we have 120 volts here, that means each bulb will have a voltage of 60 volts, since they're equal. Right? So now we say if switch S is open, okay, then what? Then if switch S is open, bulb right A and bulb B, right, are in are in series. Okay. Since they are in series, that means, what does that imply? That implies current through both bulbs is the same. Right. So if that is the situation, then we know if the current in both bulbs is the same, that would imply, right, so we got the I in bulb A, right, is equal to I in bulb B. Okay, let me just double check this. A and that's in, right, since we have a series connection. Okay, so there's one conducting path. So if that is the case there, and both resistors are equal, because they say we're dealing with identical bulbs. So therefore, we say brightness, we can say brightness, right? We can say here bulb A's brightness is equal to bulb B's brightness. So bulb A is equal to bulb B, right? But we also know that bulb C does, right, does not light up, since the circuit is not complete. Right, so now let's look at the next one. Here we have now a circuit 1 and circuit 2. Right, all have identical bulbs. But if they don't have identical bulbs, it can become a bit more complicated, but the principle is essentially the same. You'll have to work that out and then determine which bulb is brighter. So all bulbs have identical resistance of 2 ohms, and the voltage across both bulbs in the respective circuit is 12 volts. As you can see here, 12 volts, 12 volts, right? Right, now, how does the brightness of bulb A in circuit 1 compare with bulbs B and C in circuit 2? Alright, so if we look at this and we say, alright, I of A, right, is equal to, we know that if we put a voltmeter here, there, right, in parallel, that is going to read 12 volts, right? And so it's going to be 12 volts upon 2 ohms, which means the current going through this bulb is 6 amps. Right, 6 amps. Right, now this is in circuit 1, right? So let's say, okay, that's in circuit 1. let's just write it here, circuit 1. Normally I like to just put it in the subscript because then I can follow or keep track. Right, now let's look at circuit 2. Here we want to know what is the current here, so we want to determine the resistance, right? So resistance in the parallel branch would be equal to RB times RC all upon RB plus RC, which would then be equal to 2 ohms times 2 ohms all upon 2 ohms plus 2 ohms, which then means this is equal to 1 ohm. So the total resistance is 1 ohm. Right. If the total resistance is 1 ohm and we want to now determine the current in the circuit, in circuit 2, so we say circuit 2, we say okay, current in circuit 2, or like I like to do it, I say I in circuit 2, like that, and that would give me 12 volts because it's the same 12 volts, and we have 1 ohm, so therefore the current in that circuit 2 is equal to 12 amps. Okay, so current is equal to 12 amps. That means if I have an emitter here, I connect an emitter here, it's going to read 12 amps. So we know the current is going to come there and some is going to go there, but because they equal resistors, we know that here we're going to have 6 amps and here we're going to have 6 amps, right? So if I have a emitter here, it's going to measure 6 amps. If I have an emitter in series there, it's going to measure 6 amps. The total must give us 12 amps. Right, so we look at this now and we say, all right, so in this case here, therefore I in bulb B, right, is equal to 6 amps, and I in bulb C is equal to 6 amps. Okay, so if I maybe just tabulate it like this and say we got bulbs, okay, let's say we have bulbs, right, we got A, B, and we got C, correct? Then if we look at the current, right, and we look at the voltage, so in the first one when we look at it, we had 6 amps, and what's the voltage? The voltage is 12 volts. So here we got 6 amps, and the voltage across bulb is equal to 12 volts. Here when we look at B, it's also 6 amps, and the voltage across parallel branch is also 12 volts, and there is also 6 amps, and there is also 12 volts. So all of them have the same voltage and current rating here, which then implies that the brightness would be A is equal to B is equal to C. Okay, in this situation here. Right. So there you have it. Right. I could have complicated a bit more in a sense that I could have asked compare the brightness after uh, after yeah compare well, all right, no, let's leave that for now. We don't want to complicate things, so let's leave it. Right, but you need to sometimes interrogate these uh, questions and see if you can then manipulate anything to see so that you get different sort of results in a way. Because sometimes you have a problem and then you can say to yourself, but what happens if I decide to change the bulbs and they're not identical? So I want bulbs that aren't identical with different resistance. How would the brightness compare? So you can try that, and instead of having identical bulbs, maybe take one is 2 ohms and the other one is 3 ohms, and then try and work out and see if you can then work out which bulb would be brighter. And you could also take the same problem, and instead of having 2 resistors in parallel, you could have 3 resistors in parallel. Right. Okay. There you have it. And see you next time.